Morning, ladies and gentlemen. Happy Friday. Good to see you. Please, have a seat. Visitors, have a seat, please. I should tell you that Microsoft is interested in you. So they're going to be showing up at some stage with cameras because you are wonderful. But right now, we are focused on studying what can go wrong. And before we do that, we're going to start out with announcements, which you are well aware of, I think, already. Today is Friday, so homework will go up today. It is due Wednesday early and Thursday regular of next week. As usual, the midterm is the day after. On Friday, we are going to try and post solutions promptly on Thursday evening so that you have a chance to go over them. All clear? Look out in your email tomorrow. There will be a bunch of information and materials for midterm prep. In between now and then, please don't sit around saying, I have nothing to prepare, they haven't sent the stuff. You have one very important thing to do, which is to take that textbook and go through it from beginning to end and read the text, not just the code. Yes? The midterm is the time when you need the text. Okay, great. If you are interested in few on-one tutoring, please talk to your GSI, and we are trying to schedule things based on everybody's availability. Okay. Yes. Question? Yes, I agree. This is less than 2 weeks away is accurate. However, it is much more telling to say it is exactly 1 week away. Correct. Thank you. I'm glad somebody actually reads the announcements. Okay. Any other comments, questions? Okay. So what we're doing now is I'm going to give you a rapid-fire summary of what we've done, because last time we introduced a lot of terminology for some rather, straightforward ways of thinking. So you have two ways of the world, this or not this. And you have some data, and you're trying to choose, is the world this way or not this way? And so we have now some data, and I'll say it in the context of the example that we did last time. That was Mendel's genetic model. For our particular example was he had pea plants, and some of them were purple and some of them were white. You remember this? And his model was the color of the flower of a plant is like one draw made from the box purple, 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 white, the 3:1 ratio. And different plants are like draws made at random with replacement, so that there is the color of one plant doesn't affect the color of any other plant. Okay. So that was his model. And we were trying to choose between his model is good, his model's not good. Null hypothesis, the model is good because the model is a very clearly defined statement about chances. And you can compute chances under the null hypothesis, and you can say the model is good, nothing, null, nothing is going on other than chance, because there's some clear notion of what chance means in that context. The alternative is something's going on, we're not saying what it is, we don't know what it is. And so I'll just go through and say some informal statements that we have used and that you might see in other texts. Nothing is going on except chance variation. That is what is the informal understanding of what a null hypothesis is. The difference between the two distributions isn't real. Now, that is a phrase that people use, and it becomes one of these catchphrases like, saying Gesundheit when somebody sneezes. But it doesn't actually mean anything until you poke at it a little bit. So what does it mean to say the difference isn't real? It just means that it happened only because of chance, not because of some reason other than chance. And the alternative is the opposite. Okay, this is a review, so I'm going to rush through. If you have questions, I want to see your arm moving because I am not looking very, very hard. Okay, so your evidence is your test statistic, which you have to choose. You choose that to help you make the decision between this way or that. And in our example, Mendel's hypothesis was predicting 75% purple plants. We actually have some percent of purple plants, and a natural statistic was the absolute difference. So our observation, minus 0.75, absolute value. That was our statistic. Statistics are often distances, but not always. Okay, so the null hypothesis is that the sample is generated at random under precise assumptions. Informally, the difference being real, it is the difference between the model prediction and what you got in your sample. And the model prediction is measured by what you would have got had the model been true. All right, so keeping on going, this is the picture that we had last time. Forget the data that they actually got. If the model had been true, what would you have got? And here we are in a wonderful position because we've got a computer that can generate data under Mendel's model. And that's what we did. And for those samples, we had 5,000 repetitions of the process. Our statistic came out looking like this. So Mendel's model predicts that our statistic should follow a distribution that looks like this. And then our statistic was actually there on that distribution. So that dot where my cursor is where the observed statistic was, and Mendel's prediction is all over the place around that. And so now the question is, are those two consistent or not? And you know that if the data and the model are inconsistent, then you have to reject the null hypothesis. If they are consistent, then you can't reject the null hypothesis. There's not no evidence. You don't have evidence against Mendel's hypothesis in this example. So no matter how you define consistent in any reasonable way, that point is consistent with that distribution. So this test supports Mendel's hypothesis. All clear? So all of this language was introduced last time. The calculation was done last time and is similar to other calculations we've done thus far. And so now what I'd like to do is I would like to get more precise about exactly what is being done to define consistent. Okay, so I said very quickly at the end of last lecture that inconsistent has some definitions. And if you go back, we know that this is sort of visibly right in the heart of the distribution. We might have had some decisions to make if the point had been here, for example. Yep, and there's some point at which you start getting uncomfortable about whether the data are consistent with that distribution, right? And so that is the point where you start saying, inconsistent. And so there are some, and by the way, before we go on to definitions, notice that when you are in the thick of the distribution, you're not too worried. You start getting worried in the tails. So what I'd like you to think of is the proportions are areas, right? There is some area to the right of a point that makes you nervous, right? It's too small for your comfort. And so the conventions are in terms of areas of tails. And so the data are inconsistent if the test statistic is in the tail of the null distribution. Remember, that distribution is generated under the null hypothesis. So first convention, area is in the tail is less than 5%. We get upset. We say, not consistent. If they are not consistent, the data is not consistent with the null hypothesis. Which one goes? Data, hypothesis, not consistent. Which one goes? Hypothesis goes, right? Null hypothesis goes. So which do you pick? The alternative. That's what you choose. Yep. And choosing the alternative says something like Mendel's model is wrong, or the jury wasn't selected at random. And now there's something going on. There's an effect. And people get terribly excited. And there's terminology. The result is called statistically significant. If you're way out in the tails, the second convention for smallness is that the tail area is less than 1%, so you're still further out. The result is called highly statistically significant, and I have to say that these two terms are a triumph of marketing of the subject. So highly statistically significant makes everybody feel that something very important has happened. Yes? What has happened is a chance has been calculated, and that chance is less than 1%. That's what's happened. You can jump up and down with excitement if you wish, as long as you know that that is exactly what has happened. No more, no less. Everyone clear? You've seen me, I'm a very cut and dried person, so I tend not to jump up and down if I can help it. You shouldn't be as hopelessly analytic as I am. I have been criticized for being too analytic at all times. Please feel free to get excited. But in the middle of your excitement, don't forget the substance. Right? And the substance here is highly statistically significant, does not mean very important. It means somebody computed a chance in a tail, and that was less than 1%. Okay, so these conventions have just become a normal process in every application of this method. Whether it's in the social sciences or in the humanities or in the natural sciences, physical sciences, 5% or 1%, these have been taken as universal constants. But they aren't universal constants. They came from somewhere. Sir Ronald Fisher, certainly one of the great scientists of the greatest scientists of the 20th century. So look at what he is saying there. We have the duty of formulating, of summarizing, and of communicating. Isn't this data science? This is what we've been saying from day one. Our conclusions in intelligible form, in recognition of the right of other free minds to utilize them in making their own decisions. Listen to this person. He is not prescriptive. He doesn't say, it shall be thus. I say so. I am R.A. Fisher. He doesn't say that at all. He says we have to be clear and comprehensible, and then let other people make up their own minds. Such a person does not give hard and fast rules, yet the rules come from his paper. So it is worth examining what he actually said in his paper. And so here is the relevant quote. He's very clear. It's subjective. It is convenient to take 5% as a cutoff, he says. Convenient for whom? Convenient for R.A. Fisher. Great. He's not hiding it. He's not saying that this has any importance beyond that. Indeed, in 1926, he says, if 1 in 20 does not seem high enough odds, we may, if we prefer it, draw the line at 1 in 50, the 2% mark. Huh? You could. Or the 1% mark. Personally, the author prefers to set a low standard of significance at 5%. Now, I want you to look at these words. Seem. We may, if we prefer. Personally, prefers, again, subjective. He is being very, very clear that this is a matter of subjective choice. Yep. You know what happens when people read text that has numbers in the middle? You read text that has numbers in the middle. People read blah, 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 number, blah, number, blah, 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 number, blah, blah. That's exactly how everybody read this. 5% and 1% got set in stone. And people ignored the seem and may and prefer. That is why in your first pass through this way of thinking, I am giving you his exact quote and his approach so that you know that these are subjective. He knew that they were subjective. He said they were subjective, and now you know they are subjective. Yep? So these are conventions. They came from here. They are not hard and fast rules. So what we ask is every time you do a test, please present your test statistic. Please present the tail area that you actually got, and then let other people make up their minds. You can say, well, I got a tail area of 3% and I think this is small. Fine, you're free to judge that as small. But then somebody else might look at 3% and say, oh, that's huge. That's fine. They're also free to make that decision. Okay? So just provide the information rather than just the short judgment. Okay, so now that tail area. That tail area has a fancy name. It is called the observed significance level, and even statisticians can't say that fast. And so it is known affectionately as the p-value. So that's your point on the empirical histogram and all the tail area. Okay, so mark your test statistic and look at the area and the tail. Now, there is a natural question, right tail or left tail, hold your horses. For us, it's very clear which tail it is in our examples, and we'll talk about exactly which tail in just a bit. Okay, so that area is the observed significance level, and this is what you see in papers. If you read a paper where in some domain of application where a hypothesis test has been used, there's a discussion of what effect was observed, and right the last section of the paper is called methods. And it's a cryptic section. It's a tiny little piece of the paper. And somewhere in there you will see this, something like this. S is the value of the statistic. Right? So in our case, that value was, can I see? Do I know which slide it was on? Number 10. In our case, the statistic was right here, 0.00888. So we would have said our statistic, whatever we called it, is 0.00888. Okay, and so now back to slide where we were, 17. So they got that statistic, and this is the p-value that they got. Do you notice that that's less than 1%? Yep. And that's the double star. They're telling you less than 1%, highly statistically significant. That's what that, when you read that cryptic thing, that's what you're reading. If it had been, 0.032, that wouldn't have been less than 1%, but it would have been less than 5%, yes? So that would have been called significant, and you would have had just one star. And people get terribly excited about counting their stars, right? But you just need to know what this means when you see it. And so now what I would like to do is I would like to formally define this thing because, put the statistic down and look at the tail is a mechanical method, but it's not actually a conceptual definition. So now we're going to define this thing. We're going to see what it means in the context of our examples, and then we're going to see whether this method of testing can actually come up with the wrong conclusion. Okay, so the p-value is a chance. Not surprising at all. It's a proportion. And it's computed by, you've seen it computed through simulations under the null hypothesis. So it's a chance that is computed under the null hypothesis. It's a number between 0 and 1, computed assuming that the null hypothesis is true. And it's a chance to do with the test statistic, because that distribution is the distribution of what? It's the distribution of the test statistic. And it is the chance that the test statistic does what? I want to shut up, you read that. Is equal to the value that was observed in the data, or is even further in the direction of the alternative. Now, let's go back to our slide here. That was our observed statistic. No. Okay. That was our observed statistic. The p-value that we computed was the right-hand tail. You agree? So it was the chance of getting that value there, the red dot, 0.00888, and everything larger. Yep. Our definition says that value or even further in the direction of the alternative. And I would like to go through two examples to see how you decide what is the direction of the alternative, right? Then you know which tail to look at. All clear? All right. So I don't know any other way other than going to data. So what I would like to do is look at, I think I've run everything. Let me see. Okay, So this is the simulation that was on the slide. So this is Mendel's data, and we are looking at the distribution of our statistic. Now, do you remember that the statistic was the proportion purple that we observed minus the proportion that the model predicted, which is 0.75, and then absolute value? Yep? The positive distance between those two quantities. Okay, somebody remind me, what was the null hypothesis? This is Mendel's pea plants. What was the null hypothesis? That the model is good. Yep? What was the alternative? The model's not good. Right? So now what we're going to think about is, if the alternative were true, how would this distance be? If the null were true, if the model is actually good, do you expect that distance to be big or small? You've got 0.75 on the one hand, that's what the model is predicting, and you've got your actual observation on the other hand, and you're looking at the distance between these two. If the model is good, do you expect these two to be close or far away? You expect them to be close. If the model is not good, do you expect them to be close or far away? Far away. Now you have to define far, but you expect them to be bigger than you would had the model been good. Yes? So in the direction of the alternative for this statistic means large values. Yes? Hence, you find the chance of getting a statistic of 0.00888, whatever the thing we got, or more. Because if the alternative were true, this test statistic would be large. All clear? And so I'm going to pause for a second. I'm going to take questions before we run another example where we have to look on the other side. Okay. So what I'd like to do now is I would like to do an example where we are going to run a test that I am faced with every time I teach a big class. Okay, so this is a list of scores for one of my classes that had 359 students, and it's not in the textbook, but it's my Stat 134 class from last semester, spring semester. So you have one row for each student who took the midterm. Oh, well, actually, no, one row for each student. And this is the section number. There were 12 sections. Okay, so this is student number 1, student number 2, student number 3, etc. The midterm was out of 25 before you start freaking out. All clear what the data represent? So for each student, I have the label of the section that they were in and their midterm score. Okay, so here's what happens every time we run a midterm or any exam. Some student, we announce, the median score, the average score, etc. Some section is going to recognize that their section was lower. They are going to recognize that. And then that poor GSI is under fire, right? Our GSI, every other section, great. Okay, fine. Let's just see if there was such a section. Okay, so I want the mean for each section. You agree I have to group by section? Yes? And then take the mean of the other column. All right. Helps to know some programming. It really does. There you go. Okay, you take a look. Yep, section 3 was kind of grumbling. Okay, now I will tell you. The section information is available on the web. But last time, who taught what section? So I, being a statistician and knowing that I should not reveal people, have permuted the labels of the sections. So you don't know which section was. But one of the sections, which I'm here calling 3, was grumbling, right? And you can see why they were grumbling. All the rest of the sections have scores, around 15, 16, something like that, and they have 13 and a bit. Yep. Okay. Just side question. If I wanted to compute the average score of the class, can I take the average of those 12 numbers? Add up those 12 numbers, divide by 12. Would that give me the average score of the class? No, because the section sizes might be different. right? You have to account for section size. Your first project, you were doing this a lot. The population sizes were different in the different zip codes. You had to account for that. Yep? Okay, so I'll just run np.mean, and that takes my original column, all of the 359, and takes the mean of those. So the class mean is 15.5. They're at 13 2/3, and they're grumbling. And so there are two positions now. There's their position. We're grumbling something was wrong with the GSI. Okay? But there's the GSI's position. The GSI is a statistician. And the GSI says, look, you've got 12 sections, right? The class has been split 12 ways. Even if you had split 12 ways at random, one of them would have been the lowest. Yep. So perhaps this is just like the average of a randomly selected group from the class. It's a hypothesis. And you know what? We can test hypotheses. So we are going to test hypotheses. And so our two hypotheses are going to be the following. Which one is the null? There's the GSI's hypothesis and the student's hypothesis. Which one is the null? Because I've had both answers immediately. Think for a second, talk to your friend. Think about what defines the null hypothesis. Right, ladies and gentlemen, key difference between a null and alternative hypothesis. The key, one and only one key. What is it? No. You don't want to prove something right or wrong. You want to find the truth. No, you want to find the truth. You do not start out with something that you're trying to prove. That's not the difference. What's the difference? Null hypothesis, alternative hypothesis. Could you please read that, internalize it, so that you can spit it back to me at 4 a.m. when I wake you up? One of them is a complete and precise model of randomness, and the other one isn't. That's the difference. That is why you can say under the null, nothing is going on other than chance. The chance is very clearly defined. That's the difference. So now we go back to our question. The student's hypothesis is that something's the matter with that section. Right? It was bad to be in that section. The GSI's hypothesis is that if you had taken students at random from the class, then you could have got an average just like that. Now, given what we've just read about null hypotheses, which one is the null hypothesis? The GSI, and there is now no doubt, no matter of opinion, one of them is a clearly defined chance model, the other one isn't. This is how you pick which one is the null. All clear? Every single time, no matter what form the test takes. So the null hypothesis is that section 3 is like a random sample of students. Now, how many students? We need to know how big section 3 was. Shall we find out? So what am I going to use? How do I find out how big section 3 was? These are my data. I use group, yes? With no other argument, and it'll just give me how many were in section 3. Okay, so section 3 had 27 students. You can see that the sections were of somewhat different sizes. Okay, so section 3 had 27 students, and so what the GSI is saying is that these 27 students are like a sample of 27 students picked at random from the class in terms of their average score. And the students are saying, no, too low. And that's important now to pay attention to what the students are saying. The students are saying, no, this 13 2/3 is too low to have come from a random sample. That's their position. You agree? They're not just saying it's different. They're saying it's low. All right. So what we're going to do, well, you tell me what we're going to do now. Talk to your friends. What are we going to test this hypothesis? What are we going to do? Okay, all, you got a plan? What are you going to do? Take a bunch of replications. What are you going to replicate? Thank you. So I'm so glad that this has the first thing that you want to do. What are you going to do? You're going to replicate under which hypothesis? The null, because you can't under the student's hypothesis. They aren't saying anything about chances. They're just saying the section's bad. Yep. The GSI is saying something very precise. They're saying that this section looks like a random sample drawn at random, drawn from all the scores. Yep. So you draw, how many times, by the way? One replication? A single replication will be how many draws? There's a clue on the screen. One replication will be how many? It's section 3 we're worrying about. You're going to replicate section 3. Section 3 had 27 students. That's how many you're going to do. That's a decision you have to make every time you run a simulation. Right? What's one single sample? One single sample is 27 students. And then with those 27 students, what are you going to do? So now you have their 27 scores. What are you going to do? You're going to take the average. Right? That's a very natural thing to do. And then you're going to do that over and over and over, and you're going to have thousands of averages. Yep. So what we're going to do is we're going to do it once, because I want you to look at the use. Okay, so we are going to sample from these 359 students. So we're sampling from the rows of a table, and therefore the sampling method is .sample, table.sample, yes, not np.random choice. Well, I mean, we could, but table.sample is more natural here. Yep. But .sample samples how? Samples at random with replacement. And I think it's more natural here to sample without. Right? You've got these 359 students. You stick your hand in and take out 27 distinct students, because that's, in fact, that's a representative of a section. Yep. And so the code, the call to... So scores was my table of scores, .sample 27 times. The option is with replacement equals false. Right? That gives you the sample without replacement. If you just erase that, it will sample with replacement. That's what we've been doing thus far. Okay, so this will give us a table of 27 selected rows, and then this column, the first column of the table, will be the scores, and will be the array of scores, and we'll take the mean of that. Okay? Okay, so I got 12.37. 12.37. The actual section had 13.66. And the GSI is saying, look, 12.37. Okay, but now, of course, we are all saying, yeah, but do it again, yeah? And so now we do it again and again, and at this point, we don't have to belabor this point too much. So I'm just in this one cell. I like to have all my data that I need. The observed mean was 13.667 of this section. 20,000 repetitions? Oh, I don't have time. 10,000 repetitions. Okay. I got to start with an empty array of means, and then I have to run my line of code, get a new mean, and append. Yep. So this now I am going to let you go home and read and figure out. It is the exact same thing that we do every single time. Compute the statistic, append to the array of statistics that are being collected. Okay. So I'm going to run this cell first, and then we'll look at more lines. And it's chugging, and we have our results. And now that's what the distribution looks like. Okay. So let's go through and see what we did here. This is our 10,000 means that we calculated. This is a histogram of those 10,000 means. They were collected into a table called results. Okay. This p-value is a particular chance, and now I would like to talk about the calculation of that p-value. Right? So our null hypothesis was section looks like a random sample. Alternative hypothesis was this mean is too low to look like a random sample. The p-value says, under this histogram, so simulate, find the distribution under the null, and then find the chance that your statistic is this much or more in the direction of the alternative. what is the direction of the alternative here? What is the alternative saying? The average scores are low. The direction of the alternative is on the low side, that much or less. So consistently with our definition of p-value, we must look at the area to the left of this point. And that is why, if you look at our empirical p calculation, we were counting the number of means that were less than the observed mean, less than or equal to, because equal to the observed mean or below, and looking at that as a fraction of however many 10,000 repetitions that we had. Right? So the point of running this was to discuss why left hand and not right hand. Questions about that? So what did it come out? 5 and a bit percent, 5.5%. If you run it again, you'll get something else. It comes out somewhere between 5.5% and 6% when I run it, right? Okay, so now, yes? P-value, by definition, is the chance of getting the data that you got under the null, the data that you got, or something that looks more like the alternative, right? The alternative here is this is a bad section, low scores. So looking like the alternative means having a low mean, right? So having a mean as low as 13 and a bit or even lower, right? Things that look bad for the null hypothesis. Okay, so you have 5 and a bit percent. Your choice. What decision do you want to make? See? Suddenly, there's not a single right answer to this. It is your choice. Isn't it wonderful having power? Somebody give me a rule, please. I'll get the problem wrong on my midterm. It's your choice. Really. Really. If you want to stick to Fisher's, convenient cutoff, the conventions that the whole world uses, then you have to say that this is bigger than 5%. Yes? It's definitely bigger than 5%. There's no argument about that, right? Therefore, the result is not significant, and that means, which are you picking? I'm sorry? The null. Yes, you don't have evidence to say this doesn't look like a random sample. You don't have enough anyway. Yeah? So if you follow the conventional cutoff, this is not statistically significant. If you happen to think that 5.5% is small, then you can conclude that this is small, and then you would rather pick the alternative. And you can see that when you get very close to the conventional cutoff, then your head starts to go, I don't really know, and it should. Because that's not some kind of law of nature. It is only a convention. So it's up to you to decide what you do here. And it really is up to you. You have to have that confidence. But you must say, my statistic came out to be 13.6667. And to the left of that, the area is 5.67%. And then you can add your statement, I think this is small, or I don't think this is small. That's okay. But you have to give those two numbers. Everyone clear? The one thing I ask is that, you can defy convention, of course. Don't only defy convention when you don't like the result. Just watch out for that one. Don't be a rebel only the times when the conventions aren't suiting you. So try and be a little bit, neutral about this. Very good question. Is the empirical p-value different than the p-value? Yes. The p-value is the actual chance of getting a sample mean that's this much or less. This distribution isn't the exact probability distribution. It's based on only 10,000 repetitions of the sampling process. So what we have is an approximation to the p-value. It's a pretty darn good approximation, but it's not exact. To get the exact value, we would have to pick every possible sample of size 27 from 359, compute the mean, and then compute that proportion. That's a lot of samples. We don't have time. More questions? Okay, So now what I want to do is I want to start looking at a mean here. So this was our mean right here, and we're kind of saying, we'll give the guy the benefit of the doubt based on convention, right? So if the mean had been here, what would we have concluded? GSI versus the GSI's randomness hypothesis versus the student's hypothesis is something's wrong with the section. Which would you pick? Something's wrong with the section becomes suddenly more interesting to pick, yes? But what this, and of course that's what you do. But look at this distribution. This distribution was generated from random samples. And you do have some area here, do you not? So some random samples did give you means that were that small. But the minute you have a cutoff beyond which you're going to say, I don't know, I think it's the alternative, you are in trouble if your random sample actually gave you a small mean. And there what you're facing is the possibility of error. And every time you make a decision based on a random sample, there is some possibility of error. Right? There are several kinds of error, but this is one of them. That the sample was actually at random, but it came out weird, and it made you feel that it wasn't random. And so what I've done is, ignore the code, please, here, because it's a graphics code that I don't want you to be looking at. I've taken the same histogram, and I have drawn this red line is all the values of the sample mean for which you would say the p-value is less than 5%, so I'm going with the student's hypothesis. All of these here would give you trouble, and of course if they were out here, they'd give you even more trouble. Okay. And you can see that some of these are actually possible. Right? Lots of them are possible. Some of them have visible chance on this scale. So you have the probability of error. And what I'd like to do now is talk about the probability of error when you make decisions. So before I move on, can you see from that picture that you might make a wrong decision using this method? So, can the conclusion of a test be wrong? Yes, and it can be wrong in one of two ways. Here's a little grid for you. Along here is the reality. Along here is the conclusion of the test. The reality is our two hypotheses are it's this way or it's not this way. Right? So the world is either this way or that. The test also says this one or that one. So if the alternative is true and the test rejects the null, that means the test is picking the alternative, we're happy. If the null is true and the test says, I'll stay with the null, we're happy. But the other two are bad. The null is true, but the test says alternative, that's an error. The alternative is true, but the test says null, that's an error. Both of them are errors, and we are going to focus just on one of them. We are going to focus on this one. The null is true, but we conclude that it's the alternative. Right? That's when our data are very far out in the tails, and we are thinking it's the alternative when actually it isn't. And so I want to do that in the context of a coin tossing example. So I'm going to toss a coin 400 times. The object here is to test whether a coin is fair or not fair. Okay? So now I want you to sit back before the code. I'm going to toss this coin 400 times. What's a natural number to calculate based on those 400 tosses? How many heads you got? Right? And you want to compare that number of heads to what? So you're Mendel now. What does your model predict? Fair versus not fair. What does your model of fairness predict? 200 heads. 400 tosses, 200 heads. Yes? So what statistic should you be using? You're testing fair versus not fair. Yep. What statistic should you use? Proportion or the number, but what do you want to do with them? Model predicts 200. Think of the Mendel example. Model predicts 200. you have some number of heads. What should you be using as your statistic? The difference, but in absolute value. How far from 200 was your number of heads? Because your test is comparing fair versus unfair. It's not saying how unfair or in what direction unfair. It's just saying fair or not. So the natural statistic, and I'm saying natural is natural to me, but it will become natural to you, is to look at the distance between what the observed is and what the model predicts, and think about what the alternative says. The alternative says unfair, so large distance. Either way, plus or minus. So take absolute value. This is exactly our Mendel statistic. We're just using counts instead of proportions. And so what I'm going to do is I'm going to simulate. So I'm going to sample from coin. I'm going to get 400 tosses. And then I'm going to count how many heads I got. And then I'm going to append that to the number of heads. And my statistic is going to be the absolute of heads minus 200. I'm going to put that in a table, and I'm going to draw you a histogram, and it looks like that. If you have exactly 200 heads, your distance is 0, and you could get any other number of heads, and your distance grows the more heads you get, right? Or the fewer heads you get. And those of you who have done some statistics in the past should notice that this is like a bell curve that has been folded over on the horizontal axis, because you're looking at absolute distances. Right. So when will you conclude that the coin is unfair? Well, that depends on your cutoff that you're using, right? Shall we pick some weird cutoff? What did I pick in the text? Okay, so in my example, I'm going to pick 6%. You okay with 6%? You want to pick some other weird percent? You're free to choose your cutoff. Not 5. Not 5. I'm not Fisher. I'm going to pick 6, just to be ornery. Okay, so anything that's below 6, I'm going to consider to be small, and otherwise I'm going to say it's large. I'm just going to pick 6. Okay, so if I pick 6%, then which of these statistics are going to bother me? Well, this is not going to bother me. This is right here. I'm going to be worrying about the top 6% here. You agree? If you rank order these statistics, it's the top 6% that are bothersome. So this code, and you are not going to draw it, so don't worry about it. This code just tells you where are the top 6%. Right? The top 6% and beyond. This is bothersome. Right? So now I want to ask you, can a coin actually give you statistics in that? Can a fair coin actually give you statistics in that range? Yes, it can. You can see that. Yes? What's the chance that it does that? Small, correct. Say again? 6%. Exactly. Because 6% is where you start worrying. And where is the 6%? It's right here. Beyond this is 6%. Here is tiny, right? But your cutoff was 6%, so you'd reject here too. And there's one critical point right here when the area beyond is 6%. And that's where you say, nah, statistic is too big for comfort. And so the chance that you make a mistake is actually exactly your cutoff. Now, there's an extensive discussion of this in the text. I will come on Monday. I've given myself a free lecture on Monday because I knew that I would have wrap-up to do. I will come on Monday. I will discuss this issue some more, and we will see it in many contexts. And then on Monday, what I'm going to do is I'm going to go back through the text, pick examples that were done, and ask new questions about them. There will be no new code. There will be no new anything other than a new question that we can answer based on what you know, to give you, some workout in making decisions. And then Wednesday, I'll do a review of the more technical stuff like probability and so on. All okay? All right, I'll see you.